Hello everyone from everywhere you're listening to me. I'm Sosi Joel, taking you through babesiosis detection, which is our project we are doing in machine learning. All right. So below are the contents of the presentation as you see them. For the interest of time, I'm not going to peruse through everything, but you will see them there. Straight away, let's go to the background and introduction. So initially, the traditional automated parasitological detection relies on, of course, morphological thresholding, also heuristic pixel differencing, and this, of course, suffers from catastrophic false positives due to unconcentrated clinical blood smears that expose the main limitation. This results, of course, to poor performance, causes reduction of milk production, and also high mortality, meaning deaths of animals. And it's actually due to that the disease is actually misclassified since it's or confused as taken as to be plasmodium since both of them have similar rings and so on. So the introduction of our project is that manual microscopic diagnosis of these gamster stain smears resulting in too low subjective and also error prone. So babesiosis as a tick-borne disease, if it is delayed to be detected from an animal, it can lead to death. And therefore, that's why we have brought this approach of an AI-powered system that using convolutional neural networks that can help us to detect diseases in time and also accurately, accurately and help our farmers to reduce loss on their animals. So the recent trends, of course, deep learning has been the most used in the imaging analysis systems in hospitals and so on, with, of course, enablement of transfer learning. This enables high accuracy also. So the problem statements, we have our domain problem and then also the computational problem. So these blood smears have been actually analyzed by the the laboratory attendants actually. They have also the veterinary doctors. Uh, they examine these tests or samples slowly, whereby each sample can span from 30 minutes to an hour like that. Also, the confusion between Babesia and similar products, for example, Plasmodium, since they have similar rings, of course, there is confusion there and a manual work, meaning if a lab technician is not critical enough, he can actually confuse and make a vague verdict on what analysis he has made. Also, of course, we had some common co-infections. Maybe that is other tick-borne diseases. For example, we have anaplasmosis, thyroidosis, heart water, and so on. So the combinational problem was to develop an accurate multi-class classifier that will help us to group or to classify these samples from the health ones and so on. Then this will, of course, address the severe class imbalance, also enable real-time detection of the disease from the microscopic blood smears. Before me there, those are our research questions. I think for the interest of time, I cannot go through them, but mostly is to check, can we transfer learning with Babesia through veterinary grading accuracy? Then also, how can you distinguish these Babesia parasites from other samples? Then, of course, the research objectives are there as follows: to develop and train a deep learning classifier for babesiosis detection, since it's mostly confused with Plasmodium. So, going to the research contributions, of course, we developed a focused multi-babesiosis detector using our best architecture model that is efficient BNet4 on a public data set. The link to the live demo is there as follows. You can feel free to navigate it and get the best result out of it. So below in front of me here is the methodology and the system architecture. I cannot go through, but you see them where we identified, of course, the problem and analyzed it. Of course, we got contact with, we got in touch with a person doing veterinary medicine. Is a student actually in year 4, which gave us about the idea of simplifying the diagnosis process, whereby we can easily get an AI-powered system that can help veterinary doctors or lab attendants to detect the disease faster and help also in solve the problem of confusion, since this disease particularly is similar to plasmodium. So it helps them to timely get faster results and treat animals, hence reducing the mortality rate of these animals. So that architecture is there. Of course, we had our data set where we got from that source, that link there. There are different classes. There are 4 actually, as you've seen there with particular images. Then, of course, let me straight away go to the exploratory data analysis. Here, we had to explore other data sets to check what it's suffering from or what it has and so on. So here, I start with the class distribution. We had to check how many samples does our data set have. For example, we came to into conclusion and saw that red blood cells were too many compared to other 4 samples, the other 3 samples actually. Then, of course, which also checked on the imbalance ratio, where we saw Plasmodium was lagging a bit because it had a high imbalance ratio since it had the fewest number of samples in its set. Then we also checked the file size. All this helped us to come up with a strong and robust pipeline that will help us in achieving accuracy, actually. We also did, what else? We also did width and height visualizations, whereby we had to check the width and height of our samples so that we are able to come up with a nice image resolution to feed into our model for it to achieve accuracy, speed, and all that. So here we had to explore everything so that maybe we can use, remember, image resolution, you can be 224 by 224, but for particularly our model that we deployed, which was the EfficientNet B4 model arising from the EfficientNet B4 architecture, we had to use a resolution of 380 by 380, as you will see from the coming slides. So the explainable AI and analysis, of course, we came up with the confusion matrix, and this helped us to explain our results. And we shall see as it follows. I'm going to explain a confusion matrix that is coming on in front there. So as you see here, these are before training analysis. That is the training curve on my left, and so where we had accuracy and the loss. Then on my right here, we have the confusion matrix of this model, the one we deployed actually. Most of the samples were spread or were detected diagonally, meaning the model worked actually very well, whereby it detected Babesia very well. It didn't have any misclassification, even leukocyte, Plasmodium equally, but I'm seeing 8 of these samples were misclassified, whereby 6 Plasmodium cells were classified as red blood cells. Then the 2 red blood cells were classified as Plasmodium, meaning the model actually didn't suffer too much. Then below it, we have the test report, where we have the overall accuracy as 99% and other metrics. So we had different model architectures. I remember we also did that that comparison in the EDA. We also made some comparisons of it, whereby we came up with various models, including those you're seeing here in this slide, particularly. So, for example, one of my colleagues built a model on ResNet 18 architecture, and also the B4's the efficient net B4 architecture, interception architecture, VG, all these, and we were able to evaluate these results using the metrics, that is the uh, precision F1 score and recall. Then also we judge through the overall accuracy. For that case, our efficient net B4 was able to win the rest, and therefore we had to deploy it. It gave us a very good and robust model that was working very well in detecting Babesia from other classes or samples. So the demonstration of the developed product, of course, here, as you see, you're seeing this interface down here on this snipe image. You do what we call input. You drag your image there. Of course, then you submit it. The model will process it and will give you the results instantly. That's the best way I can give you how the interface, the user interface that is going to be used, or the model, how the model is going to be used. So also we did model compression, but this particular knowledge distillation. Of course, model compression refers to reducing the size of the model without compromising performance and accuracy. So as you see the image there, of course, we have the input, the teacher and the student there will be split with those soft probabilities. You will train it. The student learns from the teacher, and you finally get what we call a compressed model. You can adjust weights, of course, to match the teacher in order to achieve performance and accuracy of the teacher. So for this case, we successfully, of course, distilled the knowledge from our EfficientNet B4 to our student. Of course, the advantages of this were the faster prediction speed, of course, and also EfficientNet B4 consumed a lot of memory. So this knowledge distillation helped us to lower memory usage and also more accessibility for the field in resource limited constraint. Remember, the compressed model is a bit low weight, so therefore it can be then used in resource limited or constrained environments. So below here are the results of the compressed model. As you see, I can't read them, but the accuracy, the overall accuracy was 99% or 99.2%. Then, in conclusion, of course, we developed an automated or AI-powered system using the efficient B4. It achieved a high accuracy and also the faster image-based diagnosis from microscopic images, whereby the model was able to distinguish between the different 4 classes, and also it helped to solve the problem of confusion that raised from Babesia and Plasmodium rings. We also implemented a gradual interface, which will help us to use, which will help the users to use the model as expected. Yeah. Then for the limitations, model accuracy, of course, depends on the quality of the data set. So here we got a lot of imbalance in the class, and therefore we had to go through the EDA analysis very well and came up with a robust and nice pipeline, which helps us to develop a very good model. Of course, limitation or this model actually, or this project is limited to the GEMSA stained microscopic images only. So therefore, you have to only use microscopic images. Then also, it's not yet validated for the real world use and so on. So I think for the interest of time, those are the references that we came up through. Yeah, and that is it. Thank you for listening.